screen, just the training course optimizing pulley lagging slide?
Yeah, perfect, Dave.
Okay. All right, might make a start. Welcome to course 2 in the Optimizing Pulley Lagging Performance series. Today we're going to be looking at pulley lagging as an engineered component. The topics we're going to go through today include friction, shear stress and fatigue as they relate to lagging conveyor belt and belt splices. We're very fortunate to have Dr. Peter Robinson with us today from the University of Newcastle, and Peter's going to share the results of the work his team has been doing around friction and how friction behaves between lagging and conveyor belt around a conveyor pulley. We're also going to have a look at an engineering software tool called Lagging Select that can show whether or not the lagging and the belt is operating in what we call a safe zone. And then the last topic we'll look at is high tension bend pulleys, carry back, build up and belt cover wear and the problems that causes. The presentation today will take about 40 minutes. There'll be time for questions at the end. If you have questions as we go, please pop them in the chat. I will try and answer them at the end of the presentation. For anybody that requires or would like to use translation, there is an option for translation in either Indonesian or Thai. You can access that by selecting the round icon at the bottom of your screen. Just click on that and then click the language that you want. Talking about pulley lagging performance, lagging reliability relies on what we call the 4 pillars of lagging performance. The first pillar is lagging quality. Second pillar is lagging design. Then we have the application of the lagging, and the last pillar is lagging selection. And most of the things that we're going to talk about today revolve around lagging selection. We need all 4 of those pillars to be working properly for each application to get the best result. This is the reason that we consider pulley lagging to be an engineered part of the pulley rather than a consumable. For the first part of the webinar, we're going to look at the concept of friction, and Peter is going to take us through the work that he's been doing in this area. So I'll hand over to Peter. I'll just unshare my screen and I'll let you share, Peter. Yep, all good.
First of all, thank you for having me. As Dave said, I'm one of the researchers at the University of Newcastle alongside Color Block Solids. And we're
Peter, your audio is not very good. Have you got a microphone?
let's try that, Dave. Is that better?
Yeah, that's much better, much better.
Perfect. If it changes, just call out. I don't have a microphone, unfortunately.
No, that's a lot. What you've done, whatever you've done, has worked a lot better.
Perfect. Thanks. So we've partnered with Elastotec and a few others in this field as well, including Conveyor Dynamics and Contitech, to try and resolve what the definition of friction is around a conveyor pulley, and I suppose all of the subsequent flow-on effects that arise from defining that friction and that behavior. So obviously that feeds into optimization of the selection of lagging, optimization of lagging design and fatigue life, drive design, and also looking at how that interacts with the belt cover itself, and I think most importantly the splices in the conveyor belt. So we're partnered for about 3-4 years now, going very, very strong. And not going to lie, the deeper we dig into this topic, the deeper we realize the hole actually is. It's not a one size fits all solution, unfortunately, that we'll go through today, but it is it certainly is important research nonetheless. So the reason behind what we're doing, Dave's already touched on, I suppose, but it should come as no surprise as conveyors are certainly becoming longer and tonnages are becoming higher as well. Drive systems are now into the 8 to 10 megawatt range compared to a couple of megawatts not too long ago. Conveyors, we're still limited by about 27 kilometers in South Africa with Impumelelo, but there is designs currently being done for around the 35 to 40 kilometer mark in the UK, going through a tunnel for biofuels and fertilizers. So the increase in length of conveyors is not going to stop anytime soon. Conveyors are certainly the most preferred means of transporting bulk materials at high tonnages over longer distances. So we need to make sure that the design of the drive station is as optimized as possible, I suppose. To date, or up until a couple of years ago, when this research started, the selection of lagging, and perhaps Dave could talk more to this topic, but the selection of lagging was largely anecdotal. It was something has worked in a similar application, and basically lagging was selected based on a non-engineering approach, if that makes sense. So that kind of concept kicked off this research a couple of years ago into the idea of engineering lagging selection. And one of the most important parameters to be able to do that is understanding the loads within the contact between the belt and the drive. So to start with, what we're going to briefly talk about is what the current design methods are. Now, if you look at the ISO and DIN methods, SEMA is a little bit more extensive, but it is still based around the same principles. The current design standards utilize something called Euler's equation or the capstan equation. Now, if there's any boaters in the audience, you should be familiar with a capstan on a yacht. It's basically a stationary pulley that you wrap a rope around. And the capstan equation is this simple one here, where you've got your tight side tension is F1, your slack side tension is F2. And the difference between the two is governed by this e to the mu theta. Now, mu is your coefficient of friction around the drum, and theta is your angle of wrap. So taking quite a simplified equation, and that equation's been in existence for over 200 years now. It is one-dimensional. It's been applied with a fairly broad brush to fairly complex drive systems, if you like. So it's the same equation that we use for your serpentine belts in your cars. And by extension, just, I suppose, the biggest belt drive in the world being the conveyor belt. So, but as we certainly start to get into the 4, 6, 8, 10 megawatt range and running belts up to about an ST10 or 12,000, we are seeing these design criteria and I suppose the assumptions behind this design criteria start to crumble. And it mostly falls down to this just here. So this table, hopefully you can see my mouse, this table is a defined coefficient of friction from the standards. And you can see that they specify 4 different types of lagging. There's certainly more than 4 different types of lagging in practice now. And the coefficient of friction, if we just consider, say, dry application, is typically between about 0.35 up to about 0.45. Now, so that covers your bare steel, obviously, your poly, your rubber, and your ceramic lagging as well. So one of the assumptions of the capstan equation is, first of all, that it utilizes a constant coefficient of friction the whole way around the angle of wrap, basically from where the belt enters to where it exits. We certainly know that's not the case. And I think more importantly, we also know that friction is considerably higher than this. Now, perhaps the most common question that we get asked is, it's better to have a conservative design. And that is 100% correct, but it does have consequences. So if you look at this equation over here, the Capstan equation, if you understate your coefficient of friction mu, then they're absolutely right. You will limit the degree of slip in your drive station, and I suppose your drive will perform quite well. But a consequence of that is by reducing mu in this equation, you're increasing your F1 and F2. Okay, so your belt tension, or your belt itself, is a higher rated belt, and it's running at a much higher tension than it actually needs to. And the ironic thing is that a consequence of running the belt at such a high tension is that you're now subjecting your lagging to high fatigue cycles, and we are seeing fatigue failures in various applications. So by optimizing what that friction should be, we certainly hope that we can design drive systems that reduces the fatigue load on the lagging to prevent failure and downtime. And I suppose by extension, we can downsize components while also ensuring that the drive doesn't slip and it actually does what it needs to do. Okay. I think I've covered all of that. The approach that we have, we've developed a testing facility here at the university to directly measure the frictional behavior, if you like, between lagging and a conveyor belt. Now, this facility, it's certainly not new to the market. There is some similar research being done in the US around this topic as well. But ultimately, the principle of this is that we put a lagging sample on these two plates just here. Then on this central plate, we will mount a sample of the belt cover. It's normally about 8 mil thick, and it's bonded to a steel backing so it doesn't have flex and give. And then we'll inflate these airbags to a certain load. There's a load cell between the airbags and this frame, so we can measure the compressive force directly. And by inflating the airbags, these two frames squeeze in and they align centrally by themselves, being on the linear rails. And then installed in this tensile testing machine, we'll basically lift this crosshead up and pull the belt from within that contact. So the lagging plates are typically up to about 30 centimeters by 30 centimeters square. We've got about 12 ton of compressive force in the airbags, or up to 12 ton, which equates to about 1.3 megapascals of face pressure, which would certainly cover most of the applications out there. There's certainly applications that exceed 1.3 megapascals, up to about 1.5 to 2. And to achieve that, I suppose we can simply reduce the dimensions of the lagging. We can chop it in half, or we can reduce the width of the belt as well to increase the face pressure. Okay. So at the moment, we have a 5 ton pull force in this equipment. We're looking at upgrading that to a 20 ton pull force. And we're currently looking at the impact of our slip or shear velocity, which is basically the velocity of this crosshead up here, pulling the belt out of the contact. So it can range from very, very slow in terms of microns per minute, all the way up to about a meter per minute as well. We'll start to look at some results. I've got 4 results just in this brief presentation today. We've got the natural diamond rubber from Elastotec. We've got the polyurethane as well. Then we've got 2 types of ceramic. We've got both your direct bond ceramic and your rubber back ceramic. So let's have a look at what the results actually look like. Comparing the 4 laggings, we typically see behavior similar to this. So this is a simple friction force versus displacement graph. And also please bear in mind that that should be kilonewtons on the left-hand side instead of newtons. But basically you'll see the force increase to a point of steady state at some point. Now, the distance that it takes to reach steady state changes with the type of lagging, and the value of that steady state also changes with the type of lagging as well. So if we start with, say, the orange curve here, the diamond rubber, we're reaching steady state after about 30 to 35 millimeters of displacement. And basically this period here up to that point is a combination of slip and also shear within the lagging and belt cover itself. Okay, so obviously the contact, they start to shear, they start to deform, and they also start to slip as well. So a current focus for us is defining how that slip and shear propagates within the contact, but it's actually quite a difficult thing to measure. So if we then have a look at polyurethane, it has a slightly longer behavior, if you like. It's taking about 40 mils to reach steady state. A couple of little waves in there as well. We'll get to that in a second. When we compare the two ceramic profiles, have a look at the yellow, which is your 80% rubber-backed ceramic, compared to the purple. So we do end up with a slightly different frictional force at the end, steady state. And there's also quite a notable difference in behavior at the start. So the purple, which is your direct bond, is quite stiff. Obviously, there's not a lot of shear in the backing or the bonding method to the steel plate. So all of this at the start is shear in the belt itself or slip. Whereas in the yellow, you've got a little bit of shear in the rubber backing as well. So quite different behavior as well. Okay. So what we'll normally do is we'll test up to about 900 kPa with this set of results. And these results tested a shear velocity, which is basically the pull velocity of the belt samples, from about 0.1 up to 10 millimeters per second. Now, there's certainly some justification to select that. We looked at, I suppose, common applications, and common applications suggest that a value of about 5 millimeters per second is representative of a shear velocity around a pulley. But I suppose in the nature of not to cover all bases, if you like, we certainly have tested a bigger range of 0.1 to 10. So the results normally look like this. Now, this is just a surface plot. You can see here we've got low pressure down here up to high pressure in the top left, and we've got low velocity in this corner as well up to high velocity over here. And for the rubber lagging, the natural rubber, you can see that the coefficient of friction varies from about 0.33 up to about 1.4. So 1.4 being low normal pressure and high shear velocity. If we have a look at the ceramic, this is the direct bond, we see similar behavior, typically from about 0.4 to 1.2. There's less dependence on normal pressure, particularly at low velocities, because of that direct bond method. There's no shear in the backing of the lagging. All the shear is in the belt cover itself. So it explains why it's a little bit more flat along this edge compared to the rubber. If we then have a look at the rubber backed, you've got a little bit more flex at low velocities, sorry. And again, we're seeing about 0.46 up to about 1.3 as a coefficient of friction. And lastly, for the poly, we're seeing about 0.4 to 1.1. Now, there's a couple of little divots in there. Poly is an interesting one to test. We saw, if I just flick back to this one here, you can see that viscoelastic behavior propagating through that curve, just the waves coming and going. We certainly do see that with poly, and that is why we see these little hollows and peaks, if you like, in the poly surface. So we're still trying to dig into exactly what causes that to happen. We suspect it may be frictional temperature build up within the poly, but certainly trying to understand the source of that and how that relates to testing. The purpose of those four plots, if you like, is not so much to demonstrate what a coefficient of friction should be. It's more so to demonstrate that, I suppose, a blanket rule is that friction is not friction, and that the design standards that allow, say, 0.35 to 0.45 for all applications, we're certainly seeing about 0.35 to about 1.35, give or take. So there's quite a range in frictional behavior that isn't being captured in the design of drive systems at the moment. And I suppose it's being compensated for by running the belts at higher tension. So Just quickly on the future of this research, the testing that we're doing at the moment is currently at smallish scale. It's about 300 by 300 mil in terms of the face size. The pressures and velocities are certainly representative. We're building up to the ability to test contaminated samples and temperature other than stock standard 23 degrees. We're currently looking for facilities to test at as low as about -40, -50 degrees, and all the way up to about +50 degrees as well, just to cover all applications. Understanding how shear and creep progress within the contact is critical. And ultimately, all of this work will feed into two methods. One method is I currently have a PhD student who's looking at the viscoelastic modeling of the contact surface. He's developing various numerical models to take the raw data from these frictional tests and import them into quite a complex numerical model to design drive systems for conveyors. And I suppose the other arm of that future research is we're looking to extend the smaller scale work through the development of a large scale test facility. And that's this one just here. So this, again, has been developed between the 4 partners. It is, by all accounts, it represents a full-scale conveyor system without all the stuff in the middle. So you've got your drive pulley here and your tail pulley, but all of the friction within the conveyor is actually developed through these Haglund drives, these big orange drive units. These Haglund drives basically oppose each other, and so they generate a T1 tension or a tight side tension on one side of the conveyor and a slack side tension on the other side of the conveyor. And by locking those Haglund drives during operation, basically that tension differential will be maintained during operation. And where we utilize these series of sensors embedded in the lagging, the drive pulley, to measure exactly what those loads are as the pulley rotates. So these sensors will give us 3-dimensional forces. It'll also give us degree of slip. And from that, we can work out how friction behaves, what a coefficient of friction actually is, both around the arc of contact and across the pulley face itself. And from that, we can use that to both validate the numerical model that is being built and also downsize that to testing and validate our small scale testing. So testing at large scale, just the viscoelastic nature of the rubbers, the lagging and the belts, it does limit the ability to extrapolate from small scale testing, unfortunately. In a nutshell, that's basically what we've got in terms of the research space. Dave, I might hand back to you. And as always, I'm happy to hang around. And if there are any questions, please do send them through. You're just on mute there, Dave.
Yeah. Thanks, Peter. We'll leave the questions to the end if that's all right. I'll just share my screen again. Okay. So I want to talk now about the engineering tool Lagging Select. This is based around looking at the importance of the correct selection of lagging. These photos are a live example of a major lagging failure that occurred a couple of years ago here in New South Wales due to the wrong lagging selection. One of our large mines was going through a major upgrade in capacity from 4,600 tonnes per hour to 5,150 tonnes per hour. And they changed their main underground trunk belt from an ST 5600 to an ST 6300. But they kept using the same lagging. In fact, this particular conveyor was a dual drive conveyor. The lagging had been in operation with the ST 5600 belt for about 6 months with no signs of any problems. When the change was made to the heavier, stiffer belt, the ST 6300, within the space of 4 weeks, the lagging on both drive pulleys was very severely degraded. In fact, it went from 25 mil thick to 15 mil thick in the space of 4 weeks. As a result, the mine chose to put in their spare pulleys. Fortunately, they had 2 spare pulleys. This led to a 3-day unplanned stoppage, and the cost of production for the mine for that 3-day unplanned stoppage was $21 million. The mine asked us, or the engineers at the mine asked, well, how was the lagging selected? And it was selected the way a lot of lagging's been selected. It was selected based on experience and what had worked before, but there wasn't actually any engineering analysis behind the selection. So the next question was, well, what do we put on that will last longer than 4 weeks? And the mine was very reluctant to change to ceramic lagging because they didn't want to change the wear and the damage from the lagging to the belt. So we worked with a company called Conveyor Dynamics in the US and did a analysis to come up with a lagging that would last longer. This particular problem, the problem at this mine was basically the genesis, if you like, of the lagging select tool. We've been working, as Peter said before, for about 3 years. So it's been a collaboration between the university.
I think you just,
Sunrise.
we lost your audio for a bit there, Dave.
Sorry, you got me back?
Yes.
Yep. Sorry about that. So this lagging select tool basically just requires standard conveyor input. The input parameters are the running tensions, belt specs, the pulley details, things like the diameter of the pulley, the wrap angle, the belt cover details. We then, on the right here, can select from a range of laggings in this drop-down menu. We can also select the conveyor operating conditions, wet or dry. And from this, there's a calculation done by the software that gives two output graphs. The first output graph looks at localized slippage, and the second graph looks at fatigue and shear stresses. So this is the first graph. Just bear with me for a second. This is the graph that looks at localized slippage, and it's a graph of the normal pressure shear stress on the vertical y-axis versus wrap position across the horizontal axis, and then on the right-hand axis is friction factor. The black line, this black line here, is the contact pressure going from T1 side on the left to T2 side on the right. The blue line here is the shear stress developed in the lagging. The shear stress increases as the lagging transfers the shear to the belt around the wrap. The developed friction factor is this solid red line, and it's the ratio of shear stress over contact pressure. The dotted red line is the dry coefficient of friction, and the dotted green line is the wet coefficient of friction. And notice that these friction limits are not straight lines or constant values because the tool is using the variant friction model, which is pressure dependent. Generally, the higher the normal pressure, the lower the friction factor is. Now, when the developed or acquired friction is more than the maximum available friction, you get localized slippage, and that occurs here at this transition point. This is where the developed friction is intersecting with the friction limit. So in this example, you can see this slip zone, which is occurring basically from about 190 degrees of the wrap angle to the exit point at 210 degrees. You can see down here in the tool's graphical output, it's showing that we're using more than 100% of the available traction. and this is resulting in about 11% of slippage. Now, the tool also gives you a minimum T2 tension that could be increased. You could increase to this T2 and eliminate that slippage. And it also gives us the maximum shear stress generated in the lagging. Now, this is an important thing when you start looking at different grades of lagging, because this maximum shear stress is something that impacts on the life of belt splices. The ideal is to come up with a belt and lagging combination that has the lowest possible shear stress, has no slip, and has the required fatigue life. This second output graph is the one that looks at the stresses and the fatigue life of the lagging. The x-axis here has the average normal pressure, and the y-axis is the shear stress. This black line is the application line, which is basically the developed normal pressure and shear stress from the application entry point. So from this point here, this black line to the application exit point. The stress generated at the contact surface travels inside the lagging, and different stress magnitudes will appear at different areas of the lagging. What we then overlay in the graph is what we call our fatigue limits, which is this orange line here. Now, on the look at this picture of lagging. This is what we call the fatigue limit for the tread root of the lagging. Tread root is the bottom of the grooves in the lagging. The fatigue limit is determined through a finite element analysis. Basically, what we do is we've taken an arbitrary figure of 5 years of service life, and we basically look at the number of operating hours expected, the number of RPMs, and then we do the FEA analysis. And if the rubber in the or the design of the lagging has a fatigue life that exceeds that 5 years, then it would go on the bottom side of this this orange line. We then add in, this is the blue line is the fatigue life for the contact face. The contact face is the surface of the lagging where it's contacting the belt. You can see that in this case that the application line for the lagging, it's sitting below the blue line. So in other words, what that's saying is that you wouldn't expect within 5 years to have a fatigue failure at the contact surface. But because the black line's above the tread root fatigue limit, it's basically saying that you would not expect the lagging to last the 5 years. It will fatigue at the tread root limit. Now, there's one last area that we look at, which is this is the interface between the lagging and the pulley shell. So it's where the lagging is bonded to the pulley shell, and it's the dotted yellow line at the top. There is one other line that's not shown here, which is if you had ceramic lagging, it's the fatigue life of the bond between the ceramic and the rubber, but that's a separate graph that we won't go into today. So based on this explanation, we get what we call a safe zone. So this is this zone that's in green. It's below all of the fatigue lines. It's below the tread root line, this orange one. It's below the blue line, which is the contact face limit, and it's also below the pulley shell lagging interface, which is the yellow line. Now you can see in this example, our operational line, the black line, is sitting above the tread root. So that is basically telling us that at some point, less than 5 years, our lagging is going to fail due to fatigue at the tread root. Taking it one step further, effectively, and we've got a safe zone in green and unsafe zone in red. Now, the unsafe zone doesn't mean the lagging is going to instantaneously fail. It just means that lagging that's operating in the unsafe zone is going to fail somewhere before the 5 years due to fatigue. And then one of the printouts that the lagging select software gives you is this tread root shear stress utilization. And in this particular example, normally 100% would be the maximum. In this case, it's 1,000%. So it's way over the fatigue life limit for this particular design of lagging. Now, if we go back to this failure that we talked about before, when we did the analysis was done to try and determine the root cause, the first thing we looked at was the slippage graph. And you can see from this graph that it's not showing any localized slip. And down here, the traction limit is only at 73% of available traction. So it's telling us that slippage is not a problem, not the problem that's caused this failure. So the next thing we looked at was the fatigue graph. This is the fatigue graph for this lagging failure. Again, you can see the black operational line is sitting well above this line here is the tread root limit. So the lagging operational line fatigue line is well above the tread root limit. And you can see in the photograph the severe damage of the lagging. This is due to fatigue. So the question is, what do we now do to provide a lagging that can last longer than 4 weeks? So using this software, we analysed a wide range of laggings, and the one that came out with the best fatigue performance was a 25mm herringbone, shown here on the right. Now that you can see the graph down here, the operational line, the black line, it's sitting partially in the green zone and partially in the red zone. So it's sort of right on the borderline of that 5-year life. And what we've actually seen in service is that lagging is lasting 2 to 3 years. So it sort of aligns with what the software is telling us. Now, the mine does require, they do want lagging to last longer than 5 years. So there's actually an ongoing program at the moment to increase that lagging service life, to look at different designs. So lagging select has been developed considering just the Elastotec lagging and the conveyor design parameters. These are the people that or the companies, the organisations we're collaborating with: Tunra, the University of Newcastle, Akron Rubber Development Lab in the United States, and Conveyor Dynamics in the United States. The lagging select has been customised for the actual coefficient of friction values between Elastotec lagging and the industry grade M grade belt. And this is based on the work that Peter's just given you an introduction to. The friction coefficient values complex parameter. At the moment, all the testing that's been done has been done at room temperature, but we are now setting up to get equipment so that we'll be able to test from -40 to +60 degrees for friction coefficient, because this is important if you're putting drive systems into areas with extremes of temperature. This bond fatigue testing, that work is going to be done on, first of all, ceramic to rubber bonds, but then secondly to the bonding systems used for lagging to pulley shells. So that's hot vulcanized bonding systems, cold bond bonding systems, and direct bond bonding systems. The compound characterization, this is testing that's done to determine the fatigue life of particular rubbers. So it's been done on the Elastotec rubbers, and then also on the particular belt rubber samples that we're using. And it's unique to every rubber. It's like a fingerprint. So you can't just mix and match and look at other rubbers and assume they're the same, because they're not. They're different. The FEA analysis is being done by Conveyor Dynamics. These 4 factors are the things that make the software accurate. So I want to just quickly look at high tension bend pulleys. This is arguably the most difficult application for pulley lagging, and currently, when people are using worn conveyor belts, there's no lagging really that can last the full life or match the life of the bearings on a high tension bend pulley. We have seen quite a bit of evidence that this type of failure on high tension bend pulleys, which comes from the wear in the belt, is actually the cause of reduced belt splice life. And we're going to have a look at the reasons behind that shortly. You can see that the high tension bend pulley, the damage is usually a band in the center, and that band matches or aligns with the wear profile of the conveyor belt. You can see either side of the this wear section here, the lagging seems to be in very good condition. Same with this this picture here. So this diagram shows a typical layout for a dual drive high tension conveyor. The position of the high tension bend pulley just before the primary drive is what results in the high operating tension and the contact with the dirty side of the belt. Now, the challenge with these pulleys is that they are typically large, heavy, and very difficult to replace. And because there's no existing lagging that can last at the same life of the bearings when you've got a worn belt, changing these things out is a major problem. And there isn't a lagging that you can put on site. You can't use cold bond lagging because it just doesn't have the adhesion strength. So yeah, it's a very big problem for maintenance people. So let's just have a look at why the forces or the forces that actually cause the damage. In this case, for rubber lagging, you can see the wear profile in the pulley. From the center of the photo, we can see the lagging thickness in the center. You can see down here 23.7, up here 30.4. You're talking about a 6 to 7 mil difference. And this wear has come from the wear in the belt profile. Now, these photos on the left and right, where you can see the belt or the lagging has delaminated, there's very high shear forces caused by the wear profile in the belt. And when people put rubber lagging on conveyor pulleys, a common way to do that is with layers of uncured rubber. So multiple layers of uncured rubber, and then hot vulcanize that to the pulley. The problem is that each of the layers has a joint or a knitting line. And when you then expose it to these high localized shear forces, these joints fail. And that's the reason you get this delamination. So let's just have a quick look at how these forces occur. If we look at this graph, the bottom graph shows cord tension on the left-hand axis. Sorry, let me go back again. Cord tension on the left-hand axis, then across the bottom we've got the belt width. Now this is for a brand new belt, so no wear. And you can see the tension's uniform. If we then go to a belt profile that has 5 millimeters of belt cover wear, basically what happens is on the edge of the wear profile, you get a higher localized shear force. In the center of the wear profile, that drops down to a lower shear force. And then on the other side of the wear profile, it increases back up again. As the wear increases, so now we go to a 10 mil of belt cover wear, you can see that these peaks on the edge of the wear profile are much higher. And also the recess in the center of the wear profile is much lower. And if we look at this, the top of the peak we call the maximum localized shear stress, and the center of the bottom of the trough we call the minimized shear stress. And there's a thing that we call, we refer to for this, the ratio of the maximum shear stress to the minimum shear stress, we call the shear stress multiplier. And I'll explain why that's important a little bit later on. Now, as the wear continues, you can see no wear here wear, like in green 5 mil, in blue 10 mil wear. Sorry, my slides are jumping. And then black 15 mil wear. So as the belt cover wear increases, the localized shear forces increase as well. And this is just a just to show you the wear of the conveyor belt cover against the shear force graph. And you can see the chords in the middle here basically are going around a different diameter to the chords that are out on the edge. If we look at, this is actual data from a mine in South America. This is the thickness of the lagging graphed against the metric tons that have been carried while that lagging's been installed. And you can see the lagging started off at 32 mil thickness and has gradually reduced to the point where they've changed it down around here when it's got to about 6 mil. So you can see they've been operating, you know, at this point here, they're operating with about 26 mil differential in lagging thickness, and then on top of that you've got wear on the belt as well. So you know you've probably got close to double that in total. So what does this do to the service life of the lagging? Well, basically what happens is if you put a new belt on and you put new lagging on, to start off with, you don't have any localized shear forces, so it takes a while for the lagging to work out. And so your first installation of lagging, let's say it lasts 18 months. Now you replace that, you put the same lagging on again, but with this second lot of lagging that goes on, the belt already has wear. So the second lot of lagging is not going to last as long. You might get 12 months. Then when you come to put the third lot of lagging on, again, it's going to be faced, even if you put the same lagging on, it's facing even more wear. So the service life is going to reduce. And this just continues on with each subsequent lot of lagging. It's not that the lagging is lesser quality, it's just that it's having to deal with much higher shear forces due to the wear in the belt. The wear actually accelerates because what happens is this graph shows you, if you look at the lagging gauge differential, so this is the difference in thickness between the center of the lagging and the sides of the lagging, graphed against the difference in speed. So this is the difference in speed in the center versus the difference versus the edge. So basically, when you have no wear on the lagging, you're getting no difference in the speed. When you get 5 mil of wear, you're getting just over or about a 0.6% difference in speed in the center. 10 mil goes up to say 1.1, and so on. It keeps on increasing, and it's the speed differential that adds to the damage because you're getting slippage between the belt and the lagging. We know from studies that have been done on these high tension belts that have a significant amount of belt and belt splice damage early in the service life that this can be a result of the wear on the belt covers and the high tension bend pulley. Consider the load. This is a graph that's related to the life of steel cords in your steel cord belt. So if you consider the load or stress that can handle an infinite number of cycles without breaking, that's called the fatigue limit. So that's this line across here, the fatigue limit for the steel cords. And typically it's around about half of the ultimate strength of the steel cord. Above the fatigue limit is called the finite life region for the steel cord. So, you know, if you're operating at a tension or stress that is above this 50% of the ultimate strength, you're going to get a finite number of cycles. If you're operating below the 50%, then the steel cords should be able to operate indefinitely. Now, the design of steel cord belt usually works on having the steel cords operating at 20% of the ultimate strength of the steel cords, which should give you plenty of safety margin. So to create circumstances where steel cords move from this infinite life zone into the finite life zone, so in other words, where they break, which is what we have seen in splices, you would require a shear stress 2 to 2.5 times the design limit. So the question is, can that occur? We look at this graph is just to define what we call the chord plane differential, and it's the distance, the combined distance between the wear and the belt cover and the wear and the lagging. So we call that the chord plane differential. I just want to show you some graphs to show how these forces can magnify. So the first graph in the top left-hand corner shows chord position and chord number. So chord number across the bottom, chord position on the left-hand axis. The second graph immediately below shows chord tension versus chord number. And the graph on the right-hand side shows the stress multiplier on the y-axis and the chord plane differential on the x-axis. So these graphs are for an unworn belt and unworn lagging. So there's no increase in the localized shear stress, and the stress multiplier is 1. If we now look at a combined total of 10 millimeters of wear, here's our graph of the shear stress versus chord position. So the top of these graphs here is a figure of about 21.8 kilonewtons. The bottom in the center here is a figure of about 1.55, sorry, is a figure of about 13.998. And so the stress multiplier is the 21.8 divided by the 13.98, which gives us about 1.55 as the stress multiplier. So that's with 10 millimeters of combined wear. If we go to 20 millimeters of combined wear, the stress multiplier, the top of this peak is around about 30.46. The bottom of the trough here is 14.8. So our stress multiplier is getting up over 2. So with 20 millimeters of combined wear, so that's the wear of the lagging and the belt, we've got a stress multiplier of around 2. Remember back here, to get from the infinite life region for the steel cords to the finite region, we needed to be multiplying by 2 to 2.5 times. So we can see that with just 20 millimeters of combined wear, we're getting to that 2 times stress multiplier. Now remember, this is our lagging, so this is lagging that's operating, and before it's changed out, just the lagging on its own has 26 millimeters of wear. So if you then add that to, let's say there was a comparable amount of wear on the belt cover, you could be talking in the range of 40 to 50 millimeters of combined wear. So you can see that it would be very easy to get over a 2 to 2.5 times stress multiplier. So what do we do with high tension bend pulleys? There are several schools of thought on the best way to extend the service life of the lagging for high tension bend pulleys. One approach is to produce a lagging that is inherently stronger and more abrasion resistant than the forces that the lagging is subjected to. Examples of this are rubber back ceramic, direct bond, and hot cast polyurethane. of those three, the only one that I've seen that really can handle the very highest of belt tensions is the direct bond ceramic. And the reason for that is that the direct bond ceramic has 5 to 10 times the bond strength of these other materials, and obviously has very good abrasion resistance courtesy of the ceramic. The disadvantage with this approach is that all of those high localized shear forces are now reflected directly back into the belt and the belt splices. There's no give in this type of, hard, inflexible lagging. The second school of thinking is geared around trying to protect the belt, and it's using an abrasion resistant but soft and flexible lagging with a profile that allows the lagging to deflect under load and thus accommodate some of the high localized shear forces. The disadvantage with this type of lagging is that none of these high performance rubber laggings can actually last as long as the bearings when you've got significant belt wear and high tensions. So this is not a perfect solution, and it is an area that we are currently working to improve. So in summary, the things that we can do to improve the performance of the belt and high tension bend pulleys: we can reduce the wear on the belt cover by choosing highly abrasion resistant belt covers. These are ones with a volume loss below 30 cubic millimeters. Your standard M grade of belt cover has a volume loss of 130. So, that's going to wear much more quickly. Look at chute loading to minimize the wear of the belt, and look at your belt cleaning. Good belt cleaning will reduce the wear. Reduce the wear on the pulley lagging by going to a very abrasion resistant rubber, like what we call our extreme rubber lagging. Reduce the shear stress generated by wear on the pulley lagging by using a flexible lagging, again a rubber lagging. And the last one, which is basically what we're working on at the moment, is what we call a replaceable hot vulcanized rubber pulley lagging, which is currently under development. Now that's basically all that I've got for today. I'm going to hand over if there are any questions for Peter or myself. I'm happy to try and answer them. I've got one question. Sorry, go on.
You got one question? Oh, okay, it's Alex Gabriel here from Feather in Perth. Just a quick one. You have the mu factor, the friction factor is based on the M grade belt, but nowadays in the iron ore industry, there's barely used any M grade. So we're working with very highly abrasive resistant belt covers on the top, but also with low rolling resistance covers on the bottom, and they get further and further developed for reducing the power consumption of conveyors. So have you been in touch with any of the feather companies regarding these compounds?
I have been speaking with Bo Weiss from your Victorian office, and he's certainly, we've been talking to him about the Ultra Tough compound. Is that the one that you're referring to?
The Ultra Tough is more on the top cover, but we have also what we call we have the low resistance Power Saver 1 and Power Saver 2, and we're working on further improvements. And I just wonder, they absorb less energy. That is the main aim with these rubber compounds, which will be in contact with the pulley, but also I don't know if the friction will change, friction factor on these. I have no data about it, but it would be worth to reach out and discuss that, because we develop better and better engineered conveyor belts. And as you said, with the ST6300, you probably move then issues into the lagging area, which pop up later on and cause massive production losses. So Bo Weiss is definitely a good contact. I will definitely talk to him. But we have like Power Saver 1, Power Saver 2, and I think we work on Power Saver 3.
Is there anybody else, Alex, that we should be talking to within your organisation?
Definitely. But is our general manager for the development for technology is Tim Briggs.
Okay.
Tim and
Yep.
Briggs with BRIGGS.
Okay. All right. Thank you for that. Much appreciated.
Dave, I might just.
Okay, sorry.
I was just going to add to that. Dave, I can help facilitate a conversation with Tim Briggs and Brendan Bear in his team. Just to your point around the considerations around bottom cover selection, we have done some initial work on this. We did some initial testing looking at the variation of cover grades and on cover thickness. And we did make the decision to go forward using the M grade 8mm because there was within, please don't quote me on this, I think there might have been within about 10% variation of friction between the products that we tested. So just going forward, instead of testing the two thicknesses of 4 and 8 and it was a low rolling resistance compound and the M grade, just going forward, we opted to stay with the M grade 8.
Okay, thank you very much. So actually you've spoken to the right people already. That's good to know.
Tim's brilliant in his field. He's brilliant.
Exactly. Sorry, I have to leave now. I've got another meeting already waiting for me. But many thanks for the invite, and I'm really happy to be part of it and still learning here.
Thanks,
really
Alex. Thank you, Alex. Thank you.
Thank you. Yes.
Okay, bye-bye.
Thanks.
We've got a question here from Peter. Peter Weatherhead about the contact face fatigue failure mode. That's a good question, Peter. I actually need to speak to the guys at CDI and come back to you on that. My understanding is that fatigue on the contact face has got to do with temperature, temperature buildup, and then degradation of the rubber as a result of that. And we have seen this. So, for example, we put some of our rubber lagging on a very large high-power pulley at Chuquicamata, and that lagging were operated quite well. The pulley was pulled out after 12 months for some mechanical problems, but interestingly, the lagging hardness had gone from 65 to 85 in the space of 12 months. And it wasn't due to slip. It wasn't heat buildup due to slip. So we think it's due to hysteresis/fatigue. But I probably have to come back to you on that if I can, Peter. I'll talk to Brad at Conveyor Dynamics and try and get you a better answer of how they describe fatigue on the contact face, if that's okay.
100% fine. Thanks, Dave.
No problem.
Just
Anybody?
one question
Sorry.
from me, Dave Stree here. With your last slide, it's showing replaceable polyurethane lagging. What is that? It's under development. What is that statement is all about?
So with these high tension bend pulleys, they're typically in excess of 35 tons. Quite often they're buried in the back of the structure, and so they're very hard to remove, and you can't put cold bond lagging on them because it just can't handle the shear stresses. So at the moment, mines that have these types of pulleys are having to pull them out, which is a major exercise, and then replace them with a new pulley. So what we are working on is a lagging that has hot vulcanized rubber on a engineered steel back, but then with a mechanical fastening system that attaches the lagging to the surface. Now, with these high tension bend pulleys, you cannot drill or weld onto the shell because of problems with cracking. So we're developing a proprietary system for attaching these hot vulcanized strips onto the pulley, but in a format where they can be replaced with the pulley in situ, so that the pulley doesn't have to be removed from, from the conveyor. So that's basically the concept that's being worked on at the moment.
No, got it. So it's more of an in situ repairs rather than, yeah. Because some
But
of our pulleys.
Yeah, but it's specific. It's specific to. You wouldn't do this necessarily for low or medium tension pulleys. There are a lot of other things you can do that would be easier and more cost effective. It's purely because these things, we're running belt. We're talking about people that are running belt tensions of 2,000 kilonewtons, and big pulleys, 2 meters in diameter, 2 meters face width, and very difficult to move.
Thank you.
Any other questions? All right. Well, thank you everybody for your time, and we will circulate a recording of the session for anybody that's interested.
Thanks, Dave, and thanks, Peter. Thanks
Thanks,
once
Pete.
again for sharing. It's fantastic.
Thanks, Mark. Good to see you.
Thanks, Dave. Thanks,
Thanks,
mate.
guys.
Thanks, everyone.
So, Sylvia, I think you're on mute.
I know, I'm just saying that the AI is working perfectly. Initial
good.
it's pretty good.
Okay, fantastic. Well, you're our first guinea pig. So you're the first test on that. So it's good to know that it worked well.
Yeah.